this video we're going to have a look at bond enthalpies and how you can use them to calculate an enthalpy change during a reaction. So there's going to be some new content for A-level but some old content from GCSE for us to go over again. So what is a bond enthalpy? It's the energy required to break a bond, 1 mole of a bond, in the gaseous state. So we need to be very, very careful. So if I were to look at this chlorine molecule, remember that chlorine is a diatomic molecule. If I was to look at it like that, there is 1 bond there. And if I were to break that bond, I would end up with 2 chlorine radicals. Now we did this in the alkanes pack, but this must be in the gaseous state for it to be measuring the bond enthalpy. If it was in say a solid state, then the first energy you put in would melt it to a liquid and then you would boil it to a gas before you broke the bonds. So it's really important that it's already in the gaseous state, the high energy state, so that what you're measuring is just the bond breaking. There are always going to be positive values. Well, bonds don't just fall apart, otherwise they wouldn't exist. It takes energy to break bonds. So we're going to write that down. Energy is required to break bonds. At A-level we would say bond breaking is endothermic. That's a word we use for energy needed. So they're going to give us an indication of the strength of a covalent bond. The stronger the bond is, the larger the energy needed. And so we can say the bigger the bond enthalpy, the stronger the bond. Now, in reality, it would be a very, very big book to look in if we had the bond enthalpy for every bond. Let's just have a think about that. Imagine you've got a CH bond. But in methane, we know that there are 4 of those. Are all 4 CH bonds identical? Are they also identical to the strength of a CH bond in ethene, which is a slightly different molecule? And are they the same if I put a Cl on the chloromethane? Doesn't that affect the strength of the bond? So CH bonds aren't identical in every molecule, and therefore we'd have to have values for every single CH bond in every single molecule that exists, and that's going to take us an awful long time to look up. So what we actually do is quote mean bond enthalpies. So that is the energy required to break a covalent bond that's been averaged over a wide range. So we're using this average value rather than a specific one. Right. What we're going to do now is do the bit that you've done at GCSE, which is how would we calculate this enthalpy change? You may have called it energy change, when we know some values for the bonds. And at GCSE, you will have probably looked at, I need to break all the bonds first of all, then I'll make some new bonds, and the difference between those 2 values is going to be the energy change, or in our case, the enthalpy change. So remember that enthalpy change is delta H, because enthalpy is H and the change is the delta. We're going to add up all the energy needed to break the bonds. We're going to use this sigma to represent sum of, and then we're going to have energy required to break bonds. So we're going to add that up. And then we're going to add up, so sum of the energy required, or the energy when new bonds form. So I'm going to actually call that energy to form bonds. And the difference between the 2 is going to give us our answer. Now, you need to be a bit careful with this, because actually it's not a very good way of expressing it, because actually what you're going to be adding up is bond energies the whole time, and given that they're the energy to break, we're not really adding up the energy released, we're adding up the energy needed to break all the bonds in the products. So really we're adding up, if we draw a little diagram down here, we're adding up all the energy needed to break every single bond in the reactant. So we're going up, how much energy do I need to put in to break all those bonds? That's our first value. And then we're saying, well, if we've got the products here, we're actually adding up how much energy to break all of those, and they both end up being the same atoms. And we're saying that the difference between the two is going to give us our delta H. And so the minus sign in the middle of this calculation is actually about the fact that we're going to break all of the bonds in the reactants, but then we're going to make the bonds in the products rather than break them. And so we're coming the wrong way down here, and so we're going to minus the products arrow. And so you just need to be careful where that comes from and understand why it is bonds broken minus bonds made. Okay, so bonds broken minus bonds made. And the minus is actually all about the fact that you're adding up values for breaking both times. So let's have a go at it. Top tip here, draw it out. We've done that for you in this first example, but in an exam they might not draw out what carbon dioxide and water look like, and it's really important that you know what carbon dioxide and water look like so that you know what sort of bonds you've got present. And then what we're going to do is we're going to do our two addings up. Oops, sorry about that little flicker there. We're going to add up the energy required to break the bonds. So let's have a look what bonds we've got to break. Let's go around them with a little pen and tick them as we count them. 1, 2, 3, 4. I've got 4 CH bonds. I'm going to come back and work out what that is from my table in a minute. And then I've got, so I'm going to add it up, so we're going to add up everything we've got. Double bond O, so we've got a value in our table. I've got 2 double bond O bonds. So I'm taking account of the 2 as well, so we've got 2 in front. And we're going to add that up. So let's see from our table what the numbers are. So we've got 4 lots of 413 and 2 lots of 497. So get your calculator out and add that up. 2646 is what I got. It's the same units as in the table because we're just adding. Right, what about the bonds that we're forming? So let's go over to our other side. We've got 1, 2 C double bond O bonds. So 2 of these. And we've got how many of these? How many OH bonds? Well, there's 2. There's a 2 in front. So we've got 4 OH bonds. And then we're going to put the numbers in from the table. So 2 lots of 805 and 4 lots of 463. Type that in on your calculator. 3462. And then in an exam we would say that enthalpy change is the sum of the bonds broken minus the sum of the bonds formed, which equals 2646 minus 3462, and so our answer was minus 816 kilojoules per mole. This is an exothermic reaction, which is what you would expect for burning methane. It gets hot when you burn methane. What we're going to do now is have a look at the next example, and we're going to see how we can shrink that down in size, that calculation, because we will not get that much space in an exam. So hydrogen bromide can be formed by the reaction of hydrogen and bromine. Remember top tip number 1, let's draw it out. We've got a H, which is just a single bond to a H, Br, Br, and then we've got 2 molecules of H, Br. And what I like to do in an exam is line it up. So remember our equation goes sum of bonds broken. Well, they're the things on the left. I'm going to line up my minus sign with my arrow, take away the sum of the bonds formed, and I'll line it up underneath the chemicals that it refers to. So what have we got? We've got a HH, I'm going to put the number 438, and we've got the sum, so I'm going to bracket round it, 193, bracket round it, minus, I've got 2 because of this 2 at the front here, lots of 366. So I managed to shrink what we did on a whole page on the last example into a few lines. If you add that up, you should get minus 101 kilojoules per mole. So why don't you have a go at the next one, pause the video and let it run and have a go, and then come back and see whether you've got the right answer. So if you've managed to get the correct answer, you should have got minus 2,668 and a half. If you haven't, let's take it back step by step and have a look. So what have we got in to break? Well, we had to break 3 CC bonds. Now, if you don't draw it out, a common mistake is to say that you've got 4 of them, because there's 4 C's, but they're only connected by 3 bonds. We've got 10 CH, and we've got 6.5 O double bond O's. And a lot of people say to me, how can you have half a bond? But remember, these aren't actually for a bond, they're for a mole of bonds per mole. So we can have 6.5 sextillion of them, because that's how many is in a mole, it's a lot. We've got 8 C double bond O's, because although there's 2 in every carbon dioxide, we've got 4 carbon dioxides, and we've got 10 OH's. So make sure you're adding up the numbers and you're picking the numbers from the table correctly. So we've got one more example here to have a go at. See if you can pause the video and have a go at this one. Now, one of my top tips when you are trying to find a value is to write that in your table and give it a letter X, so that you've got something to put into your equation the same way that you have been doing. So pause the video and see if you can work this one out. So let's have a look. First thing to point out is we do actually know the answer for delta H, so we're going to be able to put that into our equation. So I've put it down here and I've highlighted it in yellow. So my bonds broken are 2 of the unknown and a O double bond O, and then I've made 4 OH bonds. I've done a little bit of algebra to work out the value of X, so my HH bond strength. Notice it's a positive number, which is what we'd expect because bond enthalpies are always positive. Takes energy to break bonds. Delta H's, the answers from the calculation aren't always positive, but the numbers in the table are always positive. One other thing I'd like to point out at the end of this little video is you'll notice that I wrote out the formula of the equation every time, and that's because if you make a silly little slip on your numerical calculations, you will still score some credit for that equation. So writing out what it is you're going to do. So explain to the examiner that you know what to do, you've just made a silly mistake in your calculation, you won't lose all your marks.